point, I'm hoping that you've already filled in the first page of your note. And I'm going to use the screencast lesson to go through the examples with you. So let's get started. So this is Newton's law here. F net equals ma. That means the net force acting on a mass or a system causes that mass to accelerate. Okay, and we talked yesterday that if that net force is unbalanced, then the object changes its motion, which is essentially what this law is saying. So we're going to go ahead and do the examples that are in the note. Example 1 says, determine the net force on the object below, then determine that object's acceleration with direction. So I've added in the diagram here. Yesterday we found the net force of this block here, so let's just do that again. F net is equal to 35, take away 15, which is 20 newtons. The mass of the block is 2 kilograms. So to find the acceleration, we're going to use our new equation, F net equals ma, and solve for a. And now you just simply plug in the net force you just found, the mass, and you get the acceleration. And there you have it. This makes sense because over here we have a net force going up on the system, which means the acceleration of the system will be in the upwards direction. In the second example it says, in an extreme test of its braking system under ideal road conditions, a sports car traveling initially at 26.9 meters per second comes to a stop in 2.61 seconds. The mass of the car with the driver is 1.18 times 10 to the power of 3 kilograms. A is asking for the car's acceleration, and B is asking for the net force needed to cause that acceleration. So with part A, you've been given a bunch of information, so I want to lay out what all of that is. So it says the initial velocity of the car is 26.9 meters per second, and if the car comes to a stop, the final velocity is 0. The time given is 2.61 seconds, and we are looking for A. So we're going to go back into our motion equation brains and find this equation here to find the acceleration of the car. Like, no surprise, everything in this course is going to be connected, so you will be seeing these equations again. So solving this, we end up getting 10.3 meters per second squared in the negative direction. So what does that mean? If we say that the car is moving this way, then the acceleration is that way. That means the acceleration is against the direction of motion, which makes sense because the car is slowing down. So the acceleration or the force acting on the car needs to act in the opposite direction of motion to slow it down. For part B, it's asking for the net force needed to cause that acceleration. Well, we're going to use our handy new equation, F net equals ma. You just found the acceleration, so we're going to plug in all of our information. And we're going to get, put negative in front of that, negative 1.22 times 10 to the power of 4 newtons, or So the net force, which is likely the braking force on the car, is 1.22 times 10 to the power 4 newtons backwards or against the direction of motion. Which again makes sense because if I'm acting to slow this car down, then my net force has to be in the opposite direction of motion. Okay? So those are pretty straightforward questions. In the next couple of examples we're going to do, we're dealing with moving systems of masses. So I'm actually going to do a separate screencast so that this lesson isn't too long. Now forget that, I'm going to just continue here. So in moving systems, we have more than one mass and a whole bunch of forces interacting within and among the system. Okay? In the case such as the one below, consider the following. A cable pulls the following train with a force of 3.7 times 10 to the power 4 newtons to the left. The train experiences a resistive force of 1.8 times 10 to the 2 newtons right. Determine the acceleration of the entire train. In other words, determine the acceleration of the system. So I've set up some steps for you to do, and I'll bring you through those right now. Step 1 is to draw a free body diagram of the system as a whole. So we're going to pretend that this train is now some big box. Okay, the whole thing comes together as one box. Consider the forces acting on that entire system. We can call that the resistive force or the force of friction, doesn't matter. Fa. Okay. Step 2 is to find the total mass of the system. So we got to take the mass of the caboose plus the mass of a car plus another car, and we get 3401 kilograms. Step 3 says set up Newton's second law, so that's the net force equals the mass times acceleration. Now we're going to go straight to the net force of the system. We're going to say that left is positive because Fa is greater. So Fa take away Fr or Ff, doesn't matter, equals the mass total times the acceleration of the system. And for step 4, you just solve for A. So I'm going to rearrange the equation by just dividing by mt. .7 times 10 to the 4, take away 1.8 times 10 to the 2, all over 3401. So the acceleration is 10.8 meters per second squared to the left, or 11 meters per second squared to the left. And you can write a sentence there. So the entire train, because of the forces acting on the outside of it, accelerates as a system. So everything moves together. Okay? It gets a little, not even, a little complicated when we get to example on the next page. Example, we'll call it example 3, even though it says example 2. But let's flip over and get to that right now. Alright, so in an investigation, students place a 0.80 kilogram cart on a table. They tie one end of a light, massless string to the front of the cart and run the string over a frictionless pulley and tie the other end to a 0.20 kilogram hanging object. Assume no friction acts on either object. It just makes things simpler for now. We'll do friction next week. A says determine the acceleration of the system, and B says calculate the magnitude of the tension force. So we have this system set up hanging around like this, and it kind of looks like it's in 2 dimensions. So what I have typed up written underneath that image is imagine the objects off of the pulley in a train-like setup as before. So I want you to imagine, because the system moves together, we can treat it kind of like we did the train. And in this case, they're all attached like this. So the string is in the middle, and the 2 masses are attached by them. I'm just going to draw that again to emphasize something about the string. Okay. Now I didn't leave a lot of room for it, but you can draw it next to the picture. A free body diagram of the car 1 is going to have the tension force coming out there. And of course the normal force and the gravitational force there. And a free body diagram of mass 2 is going to have the tension force that way and the gravitational force that way. We'll call it FG1 and FG2. When we do our analysis in this, oops, I didn't mean to do that. Undo. Sorry. When we do our analysis in this situation here, we only consider the forces in the direction of motion. So if you need to write that down, that's kind of important. Consider forces in direction of motion only. So what does that mean? That means this Fn and Fg do not contribute to the overall net force of the system because they are actually going here and here. So because the acceleration is this way, or we don't know, the motion is in that direction, then we don't actually need to consider those forces when we figure out our net force. So let's go back to the question for a second. Step 1 was to draw a free body diagram of the system as a whole, just like before. You're going to treat this as a total mass with the forces acting on it. So in the case of the system, let me just go back up here. You had a tension force there and a tension force there. And in that case of that second mass, the gravitational force was in that direction. If we line them up, this is what it looks like. Don't worry about it not pointing down at this point, but this is the direction of motion. So everything acting in the direction of motion is in green here. Luckily, the tension forces cancel out, and we only have to consider the gravitational force of the second mass as our force in our free body diagram. So that's it. That's our free body diagram of our system, because that's the only force contributing to the acceleration. Sorry about that. This screencast app, I guess when you press stop, it stops the recording as a whole and you can't continue. So that was an accident by me, but here we go. Well, we're going to continue with this question here. Going into step 2. Step 2 says find the total mass. Total mass is going to be the mass of mass 1 plus the mass of mass 2 to give you the total mass, 1 kilogram. Step 3, and you don't have to write step 1, step 2, step 3, just solve the problem. Step 3 is to write out Newton's second law, F net equals mass times acceleration. And the force contributing to the overall net force is the gravitational force on mass 2. And the total mass is what we're talking about, and the acceleration is there. So if we rearrange for A, we get Fg2 over mass total, which is m2g over mt, 0.20, 9.81 over 1.00. Which gives us 1.962 meters per second squared. And we're going to round that to 2 meters per second squared. When doing questions like this, in terms of direction, you can say to the right or down in this case, because if Fg was positive and then that was this way, then the total mass of the system, or the total system, goes in this kind of two-dimensional direction. Essentially what I'll be asking for in the future is not the direction of the acceleration, just the size, so you don't have to worry about the direction. So sorry, that was step 4 here. Okay, to solve for A. Okay, so that is the acceleration of the system, but we're now going to calculate the tension force. So for part B, for the tension, we're going to look at, because the tension force kind of disappeared when we looked at the system as a whole, we're going to look at each mass individually, because that's where the tension force is acting. So if we draw a free body diagram of mass 1 with the forces in the direction of motion, and a free body diagram of mass 2 with the forces in the direction of motion, then we can say, okay, which one are we going to choose to solve? I'm going to choose this one because it has less to deal with in terms of forces. So I'm going to use M1. I'm going to set up Newton's law. What just happened? Whoops. I'm going to set up Newton's law for this mass by itself. So Ft is the contributing force to mass 1's acceleration. And we just found the acceleration, so I'm going to plug that in. So my tension force is, and it only asks you for the magnitude, is 1.6 newtons, approximately. Okay, so if you need to go back and review part of the lesson, go ahead. On Friday, I'll be back to maybe review or go over some of these things and take up whatever homework questions you have. I will also be posting homework solutions to this later on today. Okay, so good luck with the homework, and I will see you tomorrow for Thursday's screencast lesson.